In this video lecture, we're going to discuss asymptotic notation and analysis and complexity analysis of algorithm. So what is asymptotic analysis? So basically, we're going to evaluate the performance of an algorithm in terms of input size. So what is the effect of the increase in input size to our algorithm performance? In reality, we don't measure the actual running time, but instead, we calculate the number of steps, the number of spaces needed by the algorithm to perform the process. Okay, so that's asymptotic analysis. Determine the number of steps in processing to give us an output and determine the spaces needed in our memory in doing the process. Okay, so why do we need to do this? Why do we need to analyze the performance? Basically, performance affects all criteria like user friendliness, modularity, security, maintainability, etc. If the overall performance is not good, therefore, even though it's super user friendly, even though it's super secure, no one will use it. No one will implement it. So that's why we need to analyze the performance of our algorithm and even our software. Okay. So example of analysis that we're going to do with the algorithm. So for example, given two algorithms for a task, how do we find out which one is better? So definitely, we're going to create a program. Am I right? That will be our first approach. Create a program that will run these two algorithms and then compare what will be the time to give us an output. And then we're going to conclude which is better based on the less time to give us an output. But what is the problem with this approach? One is some of the algorithm are dependent with the input. So some input will be biased on one algorithm or it will be against another algorithm. So therefore, it's not equal. So therefore, the result will be biased to other algorithm, to one algorithm. And also, when we do this, when we implement algorithm in a computer, definitely machine will have an effect with our result. Configuration of the machine will give us different result to the theoretical analysis that we're going to do. Okay, so again, lots of hardware will have an effect with the analysis. Okay, so that's why instead of doing the analysis, running it in a machine, okay, so we do the second approach, which is asymptotic analysis, disregarding what is the input, disregarding the machine that we're going to use. So it is highly solely connect to the number of steps. So there's no external factor in our analysis. Okay, so that's why asymptotic is good for analyzing our algorithm. Just the steps, just the algorithm will be analyzed, no external factor. So does asymptotic analysis always work? Yes, but not perfect. But it is the best way to analyze our algorithm. And also it helps us to determine what is the growth rate of our of the time it needs in performing a certain task. Okay, so one of one of the thing that we're going to discuss is time complexity. So it means count the number of primitive operation or steps as a function of input size. So we represent the steps as n in our equation. So let's have a certain process, and definitely this process could be run in different ways. So we have approach 1, approach 2, approach 3, approach 4, and each approach will have a different time complexity because it have each algorithm have different ways in processing. So A1 could be based on number of n. Okay, the growth is based on the number of n, or it could be n squared, n cubed, or 2 raised to n. Okay, so each algorithm has different growth rate. So in this video lecture, we're going to determine which among them, how we're going to determine the growth rate of a certain algorithm. Okay, so for example, an algorithm has a growth rate of 2n plus 5. So what will be the asymptotic notation of this? So which value has a great effect on this based on this term? Let's suppose n is close to infinity or infinity. So if it's infinity, 5 is negligible. 5 against infinity is negligible. Same as when you're going to multiply um, 2 to infinity, it's still infinity. So therefore, n is the factor that affects 2n plus 5. So we could say that 2n plus 5 is based on the order of n and determines the growth rate of this algorithm. Another example, n squared plus n plus 1, 10,000. So which term will have a great effect to this equation? Definitely n squared, because n is less than n squared, and this value is less than to a certain value of n. Okay, so again, if n is equal to infinity, so n squared is the bigger term against the other two. So therefore, this equation is based on the order of n squared. N squared is the one that dictates the time complexity of this algorithm. So on the next video lecture, we're going to determine the time complexity of each equation that corresponds to a certain algorithm. So see you on the next video lecture.